queue, setup violation, hold violation. We need not go that much deep. So to avoid all those things, we give preference to clock. So initially we'll be doing the clock design, and that is called clock tree synthesis. So the clock for all the cells will be given and the clock will be routed. Routed means the actual metal connection, how the connection is going to go. All that things will be done. So for in the clock tree synthesis, the full clock tree design will be completed. And after doing the clock tree design, we check for skew, latency. So these are the terminologies that they check to understand that the clock is reaching each and every registers and there is no timing delay and it won't be affecting our design. So all that things will be verified after the clock tree synthesis. Now once the clock is settled and clock is ready, then we do the last stage which is called routing. So routing means all the other cells will be there, right? All the other and multiplexers, all those other logics, then these macros that we have placed, all those things also should be connected. So all those connection will be happening in the routing stage. So routing, they'll be actually laying the different tracks, connections, everything will be done. And finally, this is how our database will be looking like. Once we complete this physical design, we do a verification. So actually verification is not only done here. So even after each and every stage, we do the verification. After doing our RTL design, there we do a functional verification to check whether our code is working as per our design. We also do some simulation. Simulation means actually some input will be given and we'll simulate and see whether the output is coming properly, whether what we have designed is what we are desired. Similarly, then once the RTL design is fine, then we go for physical design. Even in physical design, whatever is given in the coded format, we need to verify that the same thing is there in the physical design also. So after physical design, we have a verification. So it will be checking whether all the functions are correct. There are simulation, formal verification, static code analysis. These are the different type of verifications that they check before the chip is ready. So these two are mostly the major checks that we do in the verification stage. So one is called as design rule check or the DRC. So DRC means if we see in the right side picture on DRC. So before fabrication means when we are doing the chip design. So initially if we see it down, so these purple color, so those are the tracks. So after doing routing, all these tracks will be there. And from these tracks we can see that it is like straight metal lines, but when they go for fabrication, fabrication is done in the foundry. That means this design, it will be imprinted onto a wafer. So when this fabrication goes on, it won't be like a straight line. There might be some deviation, some extra spacing. So we should take care of that. So we should have some spacing in between. So if there are any spacing violation, once it goes for fabrication, if the chip is not working properly, then all our everything will be all the cost will be wasted. So that is the reason why we do this DRC check. So that DRC is nothing but to make it ready so that while doing the fabrication or in the foundry, there might be no errors. And all these DRC rules that will be given by the fabrication plant itself. So in this fabrication unit, they'll be having different big devices for doing the fabrication. So they'll be having some parameters, some spacings. So all that rules we'll be getting it from the foundry. And according to that rule, we need to cross-verify our design, whether it is meeting those. Otherwise, we will lead to violations. So for that, we do this DRC check. Then one more other check is layout versus schematic. That means in the net list, okay, forgot to tell, after doing that RTL design, so what is the output we get is called as a net list. So this net list, it will be having all the connections. So all this connection, we need to verify that it is same. Sometimes after doing this hardware, actually into hardware, while doing this connection, if space is not there, sometimes there might be shorts can occur. Sometimes that connections can go wrong. Some net can be connected to some other net. So in that cases, we can create some shorts, or sometimes net won't be connected. It might create opens. So if these are left there, then once we do the actual manufacturing, all these errors will come and the chip will be damaged. So we need to check that every functionality, everything is correct. So that is why we compare the net list and we also compare it with the how it is coming in the hardware. So you'll be able to understand if the connections are proper, if any connections are missing, like that. So these are the major verification checks. Then we also do other checks like IR drop. So if there are any hotspots, sometimes there might be many cells might be in the same place. So it will lead to some hotspot and it will lead to IR drop. So all those things also we'll be checking. There are now once then we come to the final stage, which is called as the tape out. So tape out, it will be having the final verification checks. Finally, all the chip functionality is ready. There are no DRC violation, no LVS violation. And once the chip is completely ready, then we are ready to send it to the fabrication plant. And this stage is called as the tape out. I'll just show one more video. So this is the CPU chip. This is just an example. So they are opening up a chip and showing how it is actually connected inside.
Focusing on the CPU and taking a look at what's inside. Here we have an integrated circuit, or die, which we'll refer to as a chip. This chip has 24 cores, a memory controller, a graphics processor, and many other sections. Within one of the cores, we can see its block diagram and the various elements. Zooming in on this multiply block, we find a layout of 44,000 transistors that physically execute 32-bit multiplication and constitute just 0.0.
So this is the big integrated circuit and they are concentrating onto a smaller part. So we saw that inside each and every block, there are many other blocks.
0.00017% of the overall 26 billion transistors in the CPU. Zooming in even further, we see layers of metal wires or interconnects, and at the very bottom are the transistors that form the basic.
So when we zoomed in deeper into that, we see that the basic one is a single transistor, and they're combining all these transistors for getting the desired connectivity.
Logic gates. Note that these layers of metal interconnects.
So all these metal connects that they are showing is what is the routing. So during routing, we are giving these connections. So that connections will be like these metal layers.
Aren't floating, but rather the empty space that you see is filled with insulating materials, thus providing structure and preventing the metal wire layers from touching. Furthermore, here we're only showing the transistors at the bottom and 5 layers of metal interconnects, with vias traveling vertically between the layers. In actuality, there are a total of 17 metal layers of wires in the CPU, and each.
On the chip, when we see it is very tiny, but actually there are many multiple layers inside. And all this design, it is not happening on a single layer. Multiple layer by layer, they are adding the design and we are creating the design. So in the lower blocks, it will be smaller, and as we go higher, it will be having larger area.
Successive set of levels uses larger and larger interconnects. At the bottom are local interconnects that move data around this 32-bit multiply.
So local means on that big chip, they will be having smaller modules. So these local interconnects, they will be doing the connections in that local part on that single small chip.
Circuit. In the middle are intermediate interconnects that move data around the core and at.
So if you see this integrated circuit, so they have highlighted one green color box. So there are multiple blocks. So this intermediate, it will be transferring the data in this small one box.
The top are global interconnects that move data around.
So that will be moving the data all around the chip. So these are the different types of interconnects.
The entire CPU. You might be wondering how small are these transistors? Zooming in again and past the interconnect layers, we find FinFETs, which are transistors whose channel dimensions are 36 by 6 by 52 nanometers, with a transistor to.
So these are the nanometers. We have heard that there are 2 nanometer, 3 nanometers. So these nanometers are nothing but this channel width. So as the channel width reduces,
transistor pitch of 57 nanometers. Clearly the transistors are incredibly small. Here's a mitochondria a dust particle, and a human hair for size comparisons. Now,
So this is just they are comparing how much small is that transistor.
You are saying something which is
So anybody have any doubts?
okay.
Now we saw how we design the chip. So for doing this chip design, it is basically all are on the tools. There are nothing into the hardware. Now from fabrication, that is the next stage. From here onwards, the hardware part will start. So for fabrication, first we have a stage which is called wafer preparation. So during the wafer preparation, all these silicon wafers. So these silicon wafers, we need to do some cleaning because each and if any dust particle is there also, it will disrupt the connections. So to avoid all that, we need to have a stage which is called wafer preparation. So they'll be doing the cleaning and everything, and the wafer will be made ready so that the design can be imprinted on it. Next, we have a stage which is called photolithography. So, from the name itself, we can understand that photolithography means passing light.
Did
So,
you forgot
so that
downstream?
we'll be having a photo mask. So, this photo mask it will be having our design. So, whatever design connections, everything is there. So, that design it will be light will be passed through that photo mask and it will be imprinted onto the wafer. So that is what happens in the photolithography. So all the geometric patterns, whatever is there from the design, it will be transferred to our silicon wafer. Then we have a stage which is called etching. So etching means it will be removing all the slices of material like metals, dielectric. So we saw that when we do the routing also, there are some portions which are having connections, some portions which are not having connections. So wherever this connection is not there, that portion will be etched away. So that is done during the etching stage. And after doing the etching, we have a stage which is called oxidation. So oxidation means we'll be placing a silicon dioxide on it. So that is just for giving the protective, or it should not be having any shorts open like that, for giving a insulation kind of thing. So for giving that insulation, we do this oxidation. So a layer of silicon dioxide will be placed on that. Then we come to diffusion. So diffusion is where we are adding the dopants. So initially we saw that the silicon itself in pure state it won't be conductivity. It won't be having conductivity. So making them conductive is by adding these dopants or introducing the impurities. So during the diffusion, all these impurity atoms. So if we need the negative N type there, our P type, accordingly the same that type of impurity will be bombarded onto the wafer, and that is how they do this diffusion stage. Now that semiconductor will become a
Hello.
conductive material. Then once all the
Yes,
connections are
yes.
there, now we need to give the connectivity between the
Yeah.
different blocks. So that is done during the metallization.
For me, I
So
don't know
metallization means they are placing thin layers of metal onto the silicon
Yeah, I
wafer,
already
and
got a
it will create
profile.
the conductive pathways. So if we have two modules for giving the
Yeah, I
connection,
already
we need some
confirmed.
metal
I'm
to
not
pass
looking
through them.
at.
So those connectivity everything will be given during the metallization. Now, once all these stages are completed, we do a wafer fabrication. Like we did in the chip design, once the chip design is ready, we did a verification. Similarly, even though everything is fabricated properly, there might be some errors. So, in the wafer inspection, what they see is on a single wafer, we'll be having different number of chips. So, need not be, it's not necessary that all will be working fine. There might be some chips that are not working fine. So in wafer inspection, they will inspect each and every chip on the wafer, whether it is working properly. So If it is not working properly, then after this fabrication itself, that chip will be discarded. Then only the chips that are functioning properly, it will be going to the next stage.
Yeah, marks and
Divya, I'll be coming to that. There are some more slides on that.
okay.
So this is the last stage. Now on the wafer, the chips are ready. Now we can't use it as such. We need to give some protection should be there. So for that, we do the stage which is called assembly, test, and packaging. So the first stage is called die attach. So die attach is nothing but now from that wafer we are cutting each and every chip. So each and every chip it should be have it, we can't simply hold a chip. So even if we touch with our hand, there are many electrical properties will happen and that chip will get damaged. So for that, first we need to do a die attach. That is nothing but just giving some support. A support is given to that single chip, and then we do wire bonding. So even it is the chip that it need to have some connection to the external. It needs to get some input from the external environment. It needs to send data. For all that, they need some connections. For that, we do this wire bonding. So we'll be creating the leads to the external environment. Now once the wire bonding is done, then we do the encapsulation. So that is that black color dye into which this chip will be placed. So it is just for giving a protective coating so that it is the external environment doesn't affect the properties of the chip. And once all this encapsulation everything is done, then we do a final inspection. So while doing this wire bonding or die attach, if anything happened or if the chip gets damaged, so that will be detected during this final inspection stage. So after the final inspection, if the chip is working fine, then we can put it into a product. So this chip, it can go either into a mobile device or a laptop or whatever is the device that we are designing it for. So this is the picture. So this is a die. So die means that chip. Then we have a lead frame. So these lead frames are the this what we saw here, die attach. So it will be put onto this lead frame just for giving a support. Then after getting that support mechanism, then they do the wire bonding. So we see that there are leads or wires that are getting connected to the external environment. And once all this is done, then we package it into this encapsulation. We'll be putting a black color covering on it, and that is how we see the chips in our real day life now. So if we open up a chip in the halfway packaging, we see that the chip is inside the center, and from the chip we have these all these connections that are coming out. So all these silver color leads that we see outside, so that are the input pins or the output pins, power pins. So it will be already designed. Even if you get the chip also, it will be having a manual. So on that manual, they'll be defining which pin is for input, which is for output. So what are the different operations? So everything will be defined. So this is how we design a semiconductor chip. So now we'll see what is the semiconductor industry landscape. So what is the different importance in modern day business? What are the different markets? What are the different applications and the new trends in the semiconductor chip design?
I'm sure it's just one doubt.
Yes.
Can I go to previous slide?
Yeah.
Previous, yeah. So like, I mean, complete this process, like how many days it will take? Normally, like.
It will take 3 months, I think. In this fabrication itself, it will take 3 months, they are telling. Even for chip design, it will take 2-3 months. So
Okay, okay.
if we are doing a project also, it is like a small module we'll be doing. In service companies, we won't be having the full design with us. Part of the design we'll be designing, then we'll send it to them. Then they will be doing the integrations. Mostly
Okay,
it
so
will take 3-4 months will be there needed.
Okay, to manufacture chip, complete chip.
Yes.
Yeah. Okay.
So these are the features of a semiconductor industry. So we know about Moore's law. So Moore's law is nothing but it states that in each and every 2 years, the number of semiconductor chips that can be added, it is doubling. So that means that chip size is reducing and we'll be able to add more and more chips. So adding more transistors onto a single chip, we are increasing the functionality. Transistor size is reducing. So on the same area, we'll be able to add more and more transistors. So in the beginning, I said that using transistors, we are creating these integrated circuits. So if the transistor size reduces, we'll be able to add more functionality. So that is what is Moore's law. So this industry is driven by this Moore's law. And that is why there are more research and development is always going on in this semiconductor industry. Then this industry is very capital intensive. So we have seen that foundries are the fabrication plants. So they need much large area for all this. And for setting up a fabrication plant, we'll be requiring 24 cross 7 energy and water. So they'll always, that power supply is needed. So if any point of time that the power supply is gone, then the full manufacturing process will be disrupted and we'll have to start it from the beginning. So setting up a fabrication plant is very capital intensive and there are not much companies that are there for this foundries. So foundries mostly, the top one is like Global Foundry and TSMC. So they are into foundry business. There are not much companies that are into foundries. So most of the companies, they are doing the chip design. So that is why this industry has to be more complex and collaborative. Complex because there are many stages like uh, we need to design the chip, do the chip design, do the manufacturing, and there should be collaboration because every industry is not building the same thing. So there might be companies that are into analog chips, some are into memory chips. So we should have some collaboration, and also there are companies that are doing only the chip design. So even if we do only the chip design, it's of no use if it doesn't come to a hardware. So we'll have to depend on companies that are having fabrication plants. So there should be more collaboration between the different companies and industries. And also this industry is very geopolitically sensitive because these are having national security, economic competitiveness. So they are having very restricted IPs and all. So it is very geopolitically sensitive.
Okay, I
So these
just
are
have
the,
a question.
yes.
Uh, yeah. So where does our scope come as software engineers? In which, which part do we play?
I think software it is coming that infrastructure, all these managing all these things. I think software is needed. So for
Yeah. So
chip,
we as software engineers on in which particular area of semiconductors do we work on?
so for this chip design and all, we need hardware engineers. Software, I think for doing the overall management, I think so. I'm not that much sure on the software part.
Okay.
Yeah.
So I was just thinking,
The
like
chip
from our
is created.
perspective.
Once the chip is created, you need to install your OS, right?
Yeah.
Yes.
Hello?
Yeah.
Yeah. So the installation of the OS and what about the code that you write and how the the micro what do we call these? What is this?
Semiconductor.
Microprocessor chips
Yeah.
interact with
Chips.
different commands in different languages. So these are all the things that we need to look into.
Okay, so we need to look into the software basically, which would recognize the commands,
Yeah,
yeah, that would be embedded on the chips.
yeah. I think this whole session is related to research and development, right?
And this
Or
is,
is it something
yeah,
somewhere
mostly.
being used?
Yeah, mostly on the semiconductor chip design. So recently we have acquired Insemi and all. I think you know. So
What is
Insemi,
the company?
yeah, Insemi technology. So they are into this chip design.
Okay.
in Bangalore.
Okay, okay, nice. Okay,
So
that's
they
a
are
great
mostly into
news.
chip design. So all these chip design stages like verification, design verification, physical design, all those we are able to do. But fabrication we won't be able to do. Chip design part we'll be able to do.
Okay,
But
so
this
this is
Moore's law,
something
but
that
which you are saying, right? Moore's law
Yeah.
is obsolete after 2014, right?
Mm-hmm.
After 2014, the
Yeah.
number of it is that Moore's law is obsolete.
Yeah, they are. I think now they are researching on other laws. I think in the last slide it is there. Some
Okay,
some
okay.
other newer technologies they are researching on that now.
Yeah.
okay, so the chip designing and all that would not be related to
Yeah,
softwares, right?
that won't
It
be.
is.
Yeah, no, that won't be related to software. Once I think all are completed, or for doing all this integration, everything, I think that time software will be
Mm.
coming. All
No,
this
software
hardware
will be
design.
required for chip design or chip design also. In the during the chip design, we
Yeah,
use softwares like MATLAB, and
yeah,
then
yes. That is there. That is mostly simulation part. When it comes to this
yeah.
hardware and all, we don't. It's not with MATLAB.
So, but
MATLAB is like simulating. We are simulating the waveform, checking the functionality. For that, we have using this MATLAB and all.
But
So
to
once we
do
come
that
to
that level of coding, you need to be basically a hardware engineer. Am I correct?
yes.
Yeah, that is
Yeah.
what my question was.
just one question.
Yeah,
So,
once the system is manufactured, right, it has to, there's something called firmware, where the microprocessor will have multiple pins, and there are options where the customer would decide which pin he wants to switch on and which one to switch off. So that will be done through the platform software, or it's called firmware. What they call it as when a microprocessor is actually manufactured, after that they call it as bring up with the board, right? So they have to boot
Okay.
it with the whatever the OS or it is. So that is where the software engineers will come and play. They are called as a bring up engineers or platform software engineering. Primarily system C is used in that area.
one
Okay.
question.
See,
One question.
what we are saying is now is the system on a chip. Microprocessor or basically fall into system on a chip family. There's something called ASIC chips also, application specific integration chips, right? So, for example, you don't need an entire microprocessor functionality for a processor that's going to sit in a car or in a washing machine. So there they will use the reduced instruction sets, and they'll make it something called microcontrollers. So those type of things will be controlled through the software. It's just typical example is your 555 timer IC, right? 555 timer IC is basically a simple chip which you can use it either you want to use it in a digital clock or even in a display board or anything. So those type of functionality will be defined by the or controlled by the software.
Curious question with quantum computing coming in, what would really change in this flow?
Current one is a binary zeros and ones, whereas quantum computing is a 8-bit operating model. I don't have much detail about that, but that will actually become a parallel computing kind of thing.
No, so what I understand is, so does it mean that you will need resistors, or how so the basic flow or process would remain the same? Is it the etching, the chip fabrication?
That and all will be same only. So when we do this designing, we are not bothered about that connect how much data like that, and all the stages will be same. All these stages what we are seeing, same stages will be coming.
Okay.
Okay, so just a question. So for each and every part of preparing the chips, I think softwares would be required. Is there any list over here or any slide wherein the particular softwares required for each and every stage is mentioned? Is there any such slide?
Software is not there. We usually use hardware tools. Like with vendors are like Synopsys, Cadence. So they will be providing hardware tools.
Mm,
Software tools I'll have to check.
okay. So then the
About
people,
tools.
like, I was just curious about like thinking, like if we have projects on semiconductors, then the resources that we need to have, they need to have hardware experience then, right? Not software experience.
Yes. Yeah, they need to have hardware experiences.
Yeah, that's right. Okay. Okay. Then that's entirely a new venture for me at least as a software engineer. Yeah. Okay. Thank you.
Yeah. So we'll see why what is the importance of semiconductors in modern technology. So we can create more innovative and product development. So this using these semiconductors, we are able to create more improved products, like for automotive systems, for advanced medical equipment. So more innovation we can bring using these semiconductors, and it will also create a competitive advantage. So if we have more competitive and more newer technology, lower nanometers. So we are seeing that nowadays that nanometers are going down, 2 nanometer, 3 nanometer. So if we are able to have more competitive advantage on the lower nodes or on the faster nodes, we can create more faster and more efficient chips. And coming to power and efficiency. So using these semiconductors, we'll be able to pack more power into smaller devices. So if we see the mobile phones, so even in the earlier mobile phones, we didn't have much functionality and the device was also bigger. But if we see our newer devices, we are able to do each and every function. So many functions are there in the smartphones or mobile device, laptops, but the size is not increasing as such. So that is the reason of having these semiconductors. And also miniaturization. So based on this Moore's law, that number of transistors. So this miniaturization that will also enable us to add more complex functionality onto the smaller devices. So these are the different markets in the semiconductor industry. So based on the components, so we can have memory chips, we can have logic chips, or analog ICs, microprocessors, microcontrollers. So based on the different type of components a company is producing, we can separate the industry. Then based on the application. So once these chips are created, to what application it is going, whether to networking, data computing, automotive, consumer, power electronics, like that. Then, based on the nanometers. So, nanometers are in that video we have seen a transistor. So, that size of the transistor, if it is 40-45 nanometer, so those are the larger ones. So, usually these higher nanometers, they are used for this military application or medical equipments, because those are bigger devices and they need not have a smaller transistor. So this bigger, larger nanometers, they will use for military applications like that. And when we come to mobiles, laptops, that time we need more lower nanometer, 5 nanometer. And if now it is not 5 nanometer, it has gone down to 3 nanometer, and even it is entering into the Armstrong era. Then based on the materials. So mostly now silicon is used, but they are also doing research on now compound elements like gallium arsenide, silicon carbide. So all these compound elements, they are able to have add up more efficiency and increase the performance. So that is why more research is now going on these compound materials also, based on the different industries. So there are companies that are into smartphones, tablets. Then some are in automobile industry. We can have ADAS system, electronic vehicles. Then in robotics or automation. Then if we come to healthcare, we can have medical devices, telemedicine. Then coming to communication, we can have network equipment, satellites, and gaming, CPU. So these are the different types of industries and the different applications that can be there. These are the new market trends that is there in the semiconductor industry. So one is technology advancement. Now we see that there are newer technologies, Gen AI, 5G, IoT. So when these newer technologies come, that is we need more higher computing power chips. So there is a surge in demand for these semiconductor chips. And also there is more focus on performance improvement. So these manufacturers, we are moving to lower nodes like 3 nanometer, 2 nanometers. So when this chip performance increases, we also need high computational power requirements also. So we have a scope of more performance improvement. by having these semiconductor chips. And there are various government strategies like US Chip Act, European Chip Act. So that is also enabling all these semiconductor chips. Then coming to smart manufacturing. So these manufacturing plants, they also have to be becoming faster, because if we need to get all these chips manufactured, it is depending on these manufacturing plants. So they are also looking into newer features like you making AI tools. So using this AI, they are trying to make manufacturing also faster, because these OEMs, so this OEM means the original equipment manufacturers, like if it is Dell, so that are the they are having that laptop. But where do they get all these components is from the semiconductor chip design companies. So only if the chip design is completed and it is manufactured, then only they will be able to get their device equipment ready. So that is why even the manufacturing part also they are trying to make them more smarter. And also there is a sustainability push. So even though we are increasing the power, increasing the efficiency, on the other side we should also take care that the carbon emissions. So when the computational power increases 2.5 times, the carbon emission is also increasing. So all the semiconductor industry, we should also have some sustainable practices. So in the fabrication plants also, sometimes they'll be having more plants nearby, or for more greenery, so that they can reduce these carbon emissions. And also high-end cyber security is needed, because there are many IPs or integrated protocols. So they are more prone to the cyber threats. So all that should be taken care. This is just an overview of how the silicon is converted into a system. So initially we have this semiconductor design. So in semiconductor design part, we do the silicon design. So that is the silicon chip design stages that we have seen. Then we come to the foundry services. So that is where this product is actually becoming into a hardware. And once even the hardware is ready, then we have this post silicon services. So once the chip design is completed, then we need to put it into a product, either into a laptop or a mobile device or an electronic vehicle, whatever it is. So that is done during this integrated product development. So we create a prototype, we need to design development, then there might be some regulatory approvals are needed, then we need to manufacture. So finally that product will be ready. So once the product is ready, then it will be launched in the market, and once it is sustainable, then comes the product sustain. So this is just a full life cycle of how a silicon is converted into a chip system. So these are the companies. So this is what I was telling about InSemi technology. So they are into the semiconductor design. So all the chip design, all the chip design stages that we have seen. So this InSemi technology is into that chip design stages. So then they are based in Bangalore mostly. Then we have Cladioscope. Cladioscope is mostly into consumer medical devices, and also Intech. Intech is into automotive and industrial. So these are the different semicon capabilities with respect to InSemi. So in Bangalore, we have acquired InSemi technology. So they are into this front end design and verification, then physical design. Then we have design for testability. So design for testability is once the design is completed, even after the design is ready, we should be able to test the chip and see whether it is functioning properly. So that is design for testability, so that the design can be tested even after the design is completed. Then foundation IP design, then post silicon validation. That is after the chip design is completed, they will be having these post silicon verification, validation checks. So all these are there in the InSemi. So now the projects, everything is mostly with the InSemi only, all these VLSI projects. So these are the expertise in InSemi. So they have this SOC expertise. SOC means system on chip. So they have they have tie up with TSMC. TSMC is Taiwan Semiconductors. So TSMC is manufacturing the chip. It is a manufacturing company. So up to 2 nanometer, and with Samsung 5 nanometer, then Global Foundry 12 nanometer. Then they are also into foundation IP business. So they have in-house design and layout capabilities. So their standard cells, analog IPs, they're able to design that. Then comes RTL to GDS2. So RTL to GDS is the full chip design. So RTL is that register transfer logic. So from that chip RTL design stage till after the routing, so all those stages, all those they have the experience. RTL stage, design verification, physical design, etc. Then domain expertise is full, like in CPU, GPUs, etc. Then there are also tools. What I said that there are various EDA tool vendors like Synopsys, Cadence, Mentor Graphics. So all these tools also they are experienced. So this is just the overview of their services. They are mostly into the design part, chip design, from the RTL design to verification, physical design, design for test, analog design, that much.
So, what is the time taken for each of these processes, and what is the lead time between the two processes?
It will take 2-3 months, I think, for finishing this chip design itself. For a single block, it will take 2-3 months. Then they need to do the integration. Then even in foundry, it will take three months. Even we thought that chip is not a single layer. There are multiple layers on top of it. So it is like a round. It takes so many times of cycles are required to complete one full chip design. Fabrication also they will take long time. At least 3 months is required. So once the chip design is ready, then we need to go send it to a fabrication plant. So if we don't have a fabrication plant with us, then we need to book also for them. Even the fabrication plants, they are having slots for each and everything. So we need to book it prior, and before that we should complete our chip design. Then we need to send it to the foundry. Then it gets completed, like that.
So, if we finish the design, and in what state can this be stored? Like, can we store it in die state, wafer state?
It is on a hardware tool. It will be like a file. So the final output that we get, it is called GDS2. So that is like a file. It will be on that system itself. We can store it. Nothing. It is not like it won't be like a hardware. Only when it goes to foundry, it comes out like a hardware. Till the physical design is completed, it is just on the tool only. So we can store it as a file itself.
This is where I think software comes into picture, right?
So these are all hardware tools mostly for this chip design completely. We are using
So
hardware.
you said it
tools.
is a file, right? It is a file means it is a software, right?
In a layman term, if you look at it, it's a software. It's a
Okay.
low-level language, right? System C, Verilog, VHDL, everything is a programming languages used to do the design work.
Yeah. True. Yeah.
But they are called as electronic design automation tools, EDA tools. They don't fall
Okay.
into
Okay.
your conventional software platform.
Okay. Got it.
To answer to Steven, are you still having any doubts? So in Infosys, mostly we are into chip design only. So we'll be having clients nowadays. Now mostly it is from InSemi. So InSemi usually their clients are like Qualcomm. So they'll be doing projects for them. So from Qualcomm and all, they'll be getting what is the design. Then they'll have to do the chip design verification, and we'll have to send it back to Qualcomm. No, we won't be having control on the full design. Only a part of the design will be sent to us. Fabrication we don't have, only chip design we are able to do. Now coming to semiconductor value chain. So this will show what are the different key players, what are the different semiconductor industry operating models, and a global value chain map. So these are the various stages in the semiconductor chip design. Pre-competitive R&D, that is research. Then after doing the research, we do the design. Once the design is ready, we go for wafer fabrication, then assembly, test and packaging, and finally distribution. So these are the different initial phases, chip design and architecture. So more high value add is coming in the design stage, because in the design stage we have control what nanometer technology we can use, what are the different optimization techniques. So all those things we have control during the design stage. So whatever optimization we need to do, everything should be done in the design stage. So that is why more value add is in the design. Once the design is ready, we send it to the fabrication plant. So there in the fabrication also, they will be having technologies like lithography, etching, and it has a moderate value add. Once fabrication is done, then we go for the assembly testing. So all this testing, packaging, everything will be done in the last stage. Once the chip is now ready, then that chip will be sent to the OEMs or the users. OEMs are the original equipment manufacturers. So they will be taking these chips and using it in their product. So these are the different things that are needed. For doing the design, we will be requiring IPs, and these IPs will be provided from the IP vendors. Then we will require hardware tools. So hardware tools are called as electronic design automation tools. So they will provide the tools that are required for doing the design. Then coming to fabrication. So in the fabrication, we will be requiring raw materials. So for doing the fabrication, we need wafers, we need lead frames, packaging, lead frames, raw wafers, chemicals. So and also we'll be requiring manufacturing equipments. So for doing all these manufacturing, there are bigger equipments. So there are various stages in fabrication like lithography, diffusion, oxidation. So for doing each and every function, they are having a big machines for doing these functions. And it is not in one round that they finish. It will take almost three months, and it will be like many times they need to circle around all the machines. Then only that full design will be coming imprinted onto the wafer. And even for doing assembly testing, there also we need raw materials and also manufacturing equipments. So these are the different companies that are there. So there are various stages, and every company is not into the same business. So there are companies, this is not a full list, just an overview of some of the companies. So there are companies which are having IPs like Imagination, then electronic design automation or EDA tool vendors, Cadence, Synopsys. Then we have Mentor Graphics, ANSYS. So there are various companies. Then using these EDA tools and IP protocols, then we come to this fabless design. So fabless design means companies that are not having a fabrication plant. Fabrication is nothing but the foundries. So they'll be doing the actual manufacturing. So there are companies like Nvidia, Qualcomm, they don't have their fabrication plant. They are more into the chip design, and they are having more hold on the newer technologies, etc. So once the design is ready, then this design is sent to the foundries. So mainly the top number one is TSMC, Taiwan Semiconductors. Then we have Global Foundry, UMC. So that those companies are only into the foundry. They don't have any control on the design. So whatever is the design that they get from these fabless company, they will do the design. And these foundries, they will be requiring raw materials like silicon, wafers. So for that, there are companies called Shijinsu, Silitron, etc. And equipment manufacturers are ASML, Applied Materials, Lam Research. So these companies will be providing the equipments. So together with that, once the design is manufactured, then we go for assembly, test and packaging. So companies like Advantest, Amcor, so they are mostly into assembly, test and packaging. Now, the last set is integrated device manufacturers. So these are the companies that have even the design and also the fabrication plant. For example, Intel, Samsung, Micron. So these companies, they are having their design also, and they also have the manufacturing plant with them. The different how the semiconductor industry has evolved. So initially we had only IDM, so the integrated device manufacturers. So the single company, they only were doing the chip design, manufacturing, everything. Then by 1960s we had these manufacturing tools, and 1970s these EDA tool vendors came. Then after that only this IDMs, they split it into fabless companies and foundries. So fabless company means they will be doing only the design. They won't be having a foundry with them. And foundries, they will be doing only the manufacturing. Then in 1990s we have IPs, and then came packaging, and finally in 2010 the software has also been added. So after I think all this integration of these things, software will be needed. So this is a global value chain map. So this just shows that everything is not done in one part of the world. So it is from different parts, different things are happening. So we'll start with the number one. In one, it is telling in UK there are some semiconductor IPs. So semiconductor IPs. Then all these fabless companies, mostly their headquarters are in US. So fabless firm. So they will have the EDA tool. Most of these EDA tool vendors also, they are also mostly in the US part only. And in US only they have these OEMs, original equipment manufacturers. So they are mostly into EDA tools and designs, that much only. But all the other things, all these raw materials, manufacturing, when all those stages come, it comes to these East Asia parts. So we can see that in India, mostly we are into design and verification.
Hello.
Then number 4.
Yeah.
In Netherlands, they have these equipment manufacturers. For doing
Okay.
this fabrication, we need heavy equipment. So all these equipments, they are manufactured somewhere in Netherlands.
Actually,
Then
my
in
profile
Germany,
got
they have
shortlisted. It's in progress.
fabrication, cleaning
My offer is
materials,
in progress.
chemicals. Then
My
in
offer
number
is in
7,
progress for
Japan, they
purchasing.
have companies that create these silicon ingots from pure silicon. Then slicing into silicon wafers. Then in China, in Taiwan, 8. In Taiwan, they have foundries. So these